In this presentation, I'm going to introduce the capabilities of risk-based inspection module of Kratos Power Inspection Solution software. This is the main menu of the software, and most important features of this menu are going to be presented. Here, at the left section, we can see location, functional groups, and corrosion groups. Location tab is where we can define our hierarchy based on factory, area, unit, equipment, component, and monitoring locations. It is important to notice that Kratos Power Inspection Solution software does the risk calculations at the component level rather than equipment level. This provides the users with the opportunity to have the equipment with the highest risk values, but also the component within the given equipment with the highest risk values as well. As a result, the user can assign most of the inspection efforts and resources to those components with the highest risk values. The second tab is functional group, which is associated with the calculation of volume of release. So we define a functional group, then we assign some equipment to this functional group, and the volume of release is automatically calculated by the software. The third tab is corrosion group. Corrosion group tab is the location where we can define or corrosion systems based on the probable damage mechanisms and also some property of the streams. The stream can be assigned from the streams available in the software, and the software has also provides the user with the opportunity to define their desired streams. So here we can add, we can edit, or we can delete or streams. Once the stream is assigned, then the pertinent values are automatically inherited from the stream that is already assigned. At the damage mechanism section, we can define our damage mechanism by the opinion of corrosion expert, whether damage mechanism is applicable or not, component damage mechanism is applicable or not, and etc. etc. So once the hierarchy is defined, corrosion groups and functional groups are defined, it is time to insert our equipments. So first, we can add equipment in the unit level. Here we can add the equipment, and then we have to add the component related to the equipment. Of course, the component has to be inserted below the hierarchy of equipment. So here we can add equipment, type of the parent equipment, and also the type of the component we are going to insert. Here for the equipment, we have general property or property section. We may add an image, and we have to consider the name. Categories column is already selected from the menu. Installation date has to be provided. A material category has to be selected from the list, and once the material category is selected, then the material specification, design category, and material type is automatically selected by the software. Then it's time to insert the operating pressure and temperature function. Then we have functional group and corrosion group that can be easily assigned from the available list that we already prepared here, for example. So I changed the corrosion group, and then you can see the corrosion group is changed. Then the dimension of the equipment has to be inserted. Here we have other tabs that is going to be explained later. Then we have to insert the related factors to the component. Here we have the component, the name. Also, there's an opportunity to insert an image. The category is already selected. Installation date, material category should be selected from the system because the material category of a component is not essentially the same as that of the equipment, and so does so do the operating temperature and pressure. Corrosion allowance should be inserted, in nominal thickness should be inserted, then the calculation of MRT, design temperature, pressure, the component diameter, it's a nozzle, so the component diameter is pretty low. Material specification is already selected. Inspection type is full RT. The joint is seamless, let's suppose, and the MRT is calculated. So now it's time to add some test points below the component level. So we may add some test point, UT test points, and then we may add some readings if we wish. Here you can see that I've already inserted 3 different measurements, and as a result, short-term corrosion rate is calculated, long-term corrosion rate is calculated, remaining life is calculated based on long-term corrosion rate. Alarming thicknesses are also calculated and provided by the software. And here we can see the graph associated with the MRWT, or minimum allowable wall thickness, or minimum required thickness, long-term corrosion rate, short-term corrosion rate, and also the points. Besides, this software has a great advantage in terms of being capable to be connected to some of the most renowned UT measurement devices, such as those products that are produced by General Electric or Olympus. Finally, we can add other monitoring locations, such as those related to corrosion coupons, again static protection coupons, different types of RT locations, and etc., and also other things. Here we may add some of them, and then we may add some monitoring. Here let's add first a monitoring location. Here we add a monitoring location, the name is this one, and then we may add some monitoring values, such as serial number of the coupon, examination date, installation date, initial weight, etc., Well, until now we have defined our hierarchy. We have inserted some equipment and components and monitoring locations. We have already defined our functional groups or corrosion groups, so it's time to get back to the main business, which is RVI calculation. So I will go through the RVI tab. Here we have general properties, or properties of the component. The values have already been inserted by user. We have qualitative risk assessment, we have semi-quantitative risk assessment, and we have attachment. So let's begin with qualitative risk assessment. Qualitative risk assessment is a very important yet equally effective measure to do a screening on a variety or a bunch of equipment to determine which equipment are going to be assessed using semi-quantitative method. Using this approach, the user can significantly optimize their time and efforts and concentrate most of the risk assessment activities to those equipment with higher estimated risk values. So here simply the user has to provide some scores for different factors related to failure damage mechanisms and also consequence related factors. So here internal corrosion is high, stress cracking is low, or so external corrosion, etc., etc. So once the equipment or a bunch of equipment is roughly analyzed using a qualitative risk, it's time to do semi-quantitative measure for those equipment with higher estimated risk values. So here in the general properties, again, we have material of construction, whether lining present or not, insulation present or not, exposed to chloride and water, processed fluid type, operating temperature, operating pressure. These are inherited from the component. But the process fluid type, the combination of process fluid type and material of construction is crucially important in the damage mechanism that the software is going to propose. And it is important to notice that the combination of these two factors has higher hierarchy once compared to the damage mechanism selected by the corrosion seeker. For example, if we assign some damage factor here, we can see amine cracking is presented here, but once we go to the component and semi-quantitative measure, because we select the process fluid type is water plus H2S, here we see no amine cracking. Once the damage factors or damage mechanisms are selected properly, the factors that contribute to the severity of the previously selected damage mechanisms are presented here automatically. Some may be applied to all of the damage mechanism, and some may be specific to each of the damage mechanism. It is important to notice that the date of last inspection thickness, minimum wall thickness is inherited from the monitoring location or the thickness measurement location that we already provided for the system here. So these values are inherited from the test monitoring location, but the rest of the factors have to be inserted by the user. Here we have internal cracking present or not, pH of the process fluid, H2S content of process fluid, whether cyanide present or not, and so and so. So these are the factors, or these are the values that contribute to the calculation of, for example, severity of stress corrosion cracking or hydrogen-induced cracking, stress-oriented hydrogen-induced cracking, and so and so. So these values have to be inserted by the user. Then it's time to insert the values that are related to the consequence of failure. Here we have representative process fluid selection, a storage phase, whether gas or vapor, atmospheric temperature, component diameter, detection classifications, isolation classification, component mass. This is different from the inventory mass. This is the component mass, for example, the mass related to the nozzle. So here we have toxicity factors. In our process fluid, we only have H2S and no other toxic fluid or toxic component is presented. So the rest are assigned to 0. And in the financial section, we have to determine the component material and the equipment outage multiplier, personal density within the unit equipment, and so and so. And once these values are inserted properly, we can simply do an RBI calculation. As the calculations are done by the software, the results are presented here. So we have area consequence results, we have financial consequence results, we have individual damage factor results. Damage factor thinning is 1, and it's quite negligible because of the last inspection date that we have already provided. This is the date we have already provided, it's today, so the damage factor is quite negligible. And then we have here we have damage factor for sulfide stress corrosion cracking, we have damage factor for hydrogen induced cracking, sulfide stress oriented hydrogen induced cracking, and so and so. And here we have the governing damage factor results. For the thinning is 1. For the stress corrosion cracking, according to API rules, the most noticeable one has to be selected as a governing damage factor. So here this value is higher, so this is transport to the governing damage factor. For the external corrosion damage factor, the condition is the same, and brittle fracture, we didn't have any brittle fracture. So it is the total damage factor, it is the probability of damage factor, it is the probability category is 1, the consequence category is D, so the risk priority in terms of area risk analysis is medium. For the financial risk analysis, again, it's medium. So for the plant date, you can see that the results are increased because of the age of the system. And here is an important feature. You can see that there is no suggestion for inspection here. Target dates results are not applicable because no inspection are needed until plant date. So there is no inspection suggestion for the software because the risk is again at the plant date is quite low. The results can also be presented in these matrices. Here we have consequence of failure area risk analysis, and here we have consequence of failure financial risk analysis. The plot can be presented here. Now we are here, and this is our plan date, and this is our risk target. So it simply can be inferred that the risk target is not going to be exceed at the plan date. But for another equipment or for another component that I have already analyzed, here we can see that as the minimum wall thickness has to be reached, and their risk values are quite higher once compared to the former component, we have some suggestion of inspection. Here we have number of inspection needed for thinning is 1, and the effectiveness is A. And the metrics and also the plot here. Now we are here, and in the plant date, the risk target is going to be exceeded. So once the risk assessment is finished, it's time to add some inspection plans. So for the inspection plan, we can add simply an inspection plan, which inspection is going to be considered for this. All the things, the kind of inspection can be selected by the user. And once the plan is done, we have also the opportunity to insert a history. History form is associated with the inspection activities that have already been done, and now we want to insert the results. Here we have the format or form for report. Different things are provided here, whether corrosion signs, deposit, and so and so, and the type of data we are going to insert can be selected. But first, it is important to notice that all the things that are provided in the report can be designed by the user in Report Designer menu. Moreover, as you can see, I can change nothing here, and I can insert nothing here. Why? Because the report has already been approved, and once the report has been approved, there is no way to change it. But for a new one, here, history, so we can add a history, right? And then we can insert anything we want. So flange pages are okay, not okay, whether we want to insert values. Maybe we want to have a selection okay, not okay, or yes or not in the corrosion signs, and we can simply design it in the report designer. And once the report is completed, it can be approved by the administrator in 1 hour for the administrator. Of course, both of these are the same because both of these things are created by my account. So here I'm the inspector as well as I'm the approver. And the report is approved. Once the report is approved, a menu for fitness for service assessment is opened. But for the reports that has not been approved yet, anything can be changed or inserted. However, there is no fitness for service assessment menu. To sum up, I introduced you the risk-based inspection module of Kratos Power Inspection solution and the way that the data have to be inserted. Using this software, the risk of different assets can be easily and accurately calculated, and this will help the clients to optimize their inspection activities and reduce the associated costs significantly. Thank you very much for your attention.